now that we've defined equivalence classes and equivalence relations, we can move on to set partitions. And set partitions actually sit parallel with equivalence classes in that they're a way of taking a set and chopping it up into pieces. And what's interesting is one doesn't actually need an equivalence class in order to do that. In fact, a set partition is a way of chopping things up, and it can be used to define an equivalence relation for us, and we'll see in a moment. So, set partitions. So notice and recall that our equivalence classes were either completely equal in that the equivalence class of 0 is the same as that of 1, the same as that as 8, they're equivalent or equal equivalence classes, or they're completely disjoint in that the equivalence class of 4 has no overlap with the equivalence class of 1. Okay, so they form these nice little connected little cliques like this. So let's prove that they must either be equal or completely disjoint. They can't have a little bit of overlap. So let R be an equivalence class on A, and let A and B two elements of A. Then the equivalence class of A is the same as that of B, or they're completely disjoint. So we need to prove this, and the proof's not actually that difficult. So let's take A and B and A and consider this intersection. Okay, so the intersection between two equivalence classes. Now, either that intersection is empty, which is one of the things we'd like to prove, or it's not empty. If it is empty, we're done, because that is 1/2 of our proposition. Okay, so that's good. On the other hand, if it's not done, then there must be some element C that sits inside that intersection. Well, C is in 1/2 of the intersection, it's in the other half. So that is, C is in the equivalence class of A, and it's in the equivalence class of B. So because it's in the equivalence class of A, we know CRA, and because it's in the equivalence class of B, we know CRB. Now, by symmetry, we also know, we can flip that around to get ARC. But then we can put together ARC, CRB, using transitivity to get ARB. And then the theorem that we proved in the last video tells us that the equivalence classes are the same. It's not so hard to prove that the equivalence classes are disjoint or identical. Now, just to change gears slightly, let's think about what that does to a set. It takes a set, like the schematic one we have here, and cuts it up into pieces like this. Okay? And then each of these pieces are disjoint, but at the same time, they completely cover the set. So let's make a more rigorous definition of that. A partition of a set A is a set of subsets, so a set of non-empty subsets of that set. So we just take a set, chop it up into pieces. Well, in particular, every element of A must be in some part of the partition. Okay, so we have our partition, so a set of subsets, and no matter which element of A, the original set we pull out, there is some piece in our partition so that that element X is sitting in that piece. So this is a rather formal way of saying every piece is in a part of our partition. Further, if we take out two parts of our partition, then their intersection is either empty or the pieces are the same. So that is, the pieces of our partition of the set are either identical to each other or they're completely disjoint. So the elements of that partition are called parts or pieces. Okay? So it's this idea that we can take a set and chop it up into pieces. Every element of the set is in one piece, or in a piece, and the pieces don't overlap at all. And this should sound familiar because this sounds exactly like what an equivalence class does. So, in particular, equivalence classes do form a partition. So, here's our theorem. Let R be an equivalence relation on A. The set of equivalence classes forms a set partition. So we need to prove that. So scratch work. Well, we said the set of equivalence classes, so this is going to be, our partition is going to be the set of all the equivalence classes in A. And of course, remember, many of these are redundant because lots of these things will be either identical or disjoint. That was what we proved about equivalence classes. So now, we need to show, in order to be a partition, back here on the previous slide, our definition, that every X in A belongs to some part of our partition. So that is, each X in A belongs to some equivalence class. We already proved that. We proved that last time. Okay? So we already know that every element of A belongs to one of these pieces. Then we also just showed in the previous little result that if we take two parts of our partition, that is, we take two equivalence classes, then they are either completely disjoint or they're identical. So we've proved the two results. We just need to put it together. Oh, flipping the wrong way. So here's our proof. Equivalence classes form a set partition. Define our set partition to be the set of all these equivalence classes. Then we proved previously that if we pull out some element of the set, that it's in its own equivalence class. And since every equivalence class is sitting inside our partition, we know that X is in some piece of the partition. One bit done. Now, we can pull out two pieces of our partition, then by the previous result, we know that those pieces have to be the same, or they have to be disjoint, because all those pieces are equivalence classes. And so these two conditions, everything is in some piece, and the pieces are the same or disjoint, is exactly what we need to form a set partition. So equivalence classes are a way of chopping up a set into pieces. Of course, they have lots of other structure because they come to us from relations, but we can actually go further. We can go the other way. In particular, given a set partition, we can use that to define an equivalence relation. So if you take a set and you chop it up into pieces, we can use those pieces, the set partition, to define a new equivalence relation. So here's a theorem that tells us that. So let P be a set partition of A. Then we define a new relation by saying that X is related to Y if there is a piece of our partition so that X and Y are in the same piece. So that is, X is related to Y if X and Y are in the same piece of the partition. And if we define a relation this way, it's a perfectly good relation. It's a subset of the pieces, or the Cartesian product of the pieces. Then we can go further and show that this relation is in fact an equivalence relation. And I'm not going to do that here. In fact, it makes a very good exercise. Maybe we'll end up doing it in class.